Hello everyone, and welcome to another tutorial video. Now we're going to be talking about setting up a transient structural analysis within Ansys Workbench. This, be forewarned please, is a more complex and involved process, so I would encourage you to refer to the previous tutorial videos before trying to attempt this level of complexity of simulation model. As the previous videos will kind of build upon a lot of the foundational knowledge required to do something that's this complex. So we're looking at a transient structural analysis. By the end of this, you should be able to set up an analysis where you can investigate the time-varying stress distribution in a component, such as this rotating single-cylinder crankshaft from a single-cylinder internal combustion engine. And you can see obviously the varying stresses as a function of the radial position or the rotation of the crankshaft itself, and the complexity involved in the kinematics of the motion as well as the kinetics of the force distribution within the component. So the first thing that I will say is that these models, because they're time varying and there's steps and increments involved in actually performing the analysis or performing the analysis result computation, they take a lot longer to run versus a static structural step that we would have looked at in the past. So I won't be running the simulation live in front of your eyes here. There will be some pausing and fast forwarding for the sake of time. These models don't take seconds or minutes to run, they take minutes or hours to run. And you can appreciate the complexity that's being shown here. This isn't as complex as it can get, but obviously it's showing kind of the simulation that you might want to perform on an internal combustion engine component. So I guess without further ado, we'll get started. We'll look at a few different iterations of the model. One of the most important aspects of tackling any analysis model that's really complex is to build upon known quantities and understand all of the analysis ingredients or the inputs that are going into your analysis model and build upon things that you know work. So if you are comfortable with doing a static structural step, try and do that to get a rough estimate. Although it's not applicable in a rotating component such as this crankshaft, try and do that to get a rough estimate on where the stresses might lie if you took a freeze frame of whatever load case you're trying to evaluate here. So that's one thing to keep in mind. The second thing to keep in mind is the fact that often the load case development in these transient simulations and understanding those analysis inputs, it takes much expertise and many hours, if not months, years of someone's career to fully understand where these load cases are coming from. And often that's more important than performing the analysis setup itself, because having good input data is the key to replicating reality and simulating the physical phenomenon that you're trying to look at. So if we look at a typical internal combustion engine pressure versus volume diagram, this is beyond kind of what we would be looking at in the core, or I guess in this scenario here. But a typical pressure volume diagram, just for some background, looks like this. As the engine is going in, the piston is moving down, the engine's going through its 4-stroke cycle here. You can see that I'll just animate the slide here so you can see as this happens. So we draw down on the piston to create a slight vacuum within the cylinder, and that draws air into the cylinder. We're not really concerned with this stroke. Then we begin to close the intake valve and start to compress the mixture. This is where we are concerned with simulating, because the forces and pressures are going up within the cylinder. So this stroke here we're interested in simulating because the forces are very high, and then we ignite the mixture, combustion happens, and the forces are now starting to decay, or the internal pressure within the cylinder is starting to decay because we're recovering all that work here as the piston moves down. So the piston traveling up in that compression stroke and then down in that expansion stroke, or sorry, the power stroke, is what we are going to actually simulate here. So there's typical pressure volume traces versus crankshaft angle that you can look at for a spark ignition engine. You can see 3 different versions here for regular combustion during an engine knock event with some erratic combustion behavior, and then pre-ignition where everything's kind of that pressure spike is phased earlier than normal, or it should be. But idealized, we have this type of pressure versus crankshaft angle curve or response. So digitizing this, we just brought this into Excel to look at that same data, and we basically digitized it in increments of 5 degrees here. So between 0 and 360, we're calling 0 bottom dead center prior to the compression stroke, 180 is at top dead center, and 360 is at bottom dead center again. So you can see as the mixture is getting compressed, and then as we start going towards top dead center, we ignite the mixture and the pressure spikes and reaches its peak. But how do we convert this pressure into a force? Because in the analysis we'd like to input a force. So assuming a born stroke of this engine of 86 millimeters and 107 millimeter of stroke, we can get 625 cc's of displacement. But from that area that the bore is covering, we can calculate the force as a function of that crankshaft angle. To get the engine parameters, we are working with this CAD file here, so we can just simply measure some dimensions that we would like. So let's say we want to measure these 3 things, the distance between here and here. We'll just reset this. We'll click measure in SolidWorks, and we'll select the 2 faces that will give us the vertical distance here of 53.8 is the radius, so double that will be the stroke of the engine. But that allows you to get kind of acquainted with the CAD geometry. The connecting rod is attaching here, and there's some main bearings here and here. So that's where the load case comes from. We'll kind of touch on this a little bit more, but basically these values we're going to need to input into Ansys. So we'll go ahead and boot up Ansys Mechanical here, and we have our workbench open where we can double click on our transient structural analysis, which is what we want to do. That's because it's a time varying structural analysis. So I'll just show you how to set up some of these ingredients, and then I'll run the model off video and we'll just review the results together. But the model itself can be run a variety of different ways. Like I said, the first thing that you want to do is just start with a known quantity. So we're simulating the engine at a certain RPM here. So we can say that we have to input the force versus time of some load response or some load signal that we want to input into the device. So we can assume, let's say 600 RPM, and we will get this load versus time here in milliseconds, and that would correspond to the following result. I have that open right here, I believe. So this is what it would look like if we were only applying the force and not actually rotating the crankshaft. So what do I mean by just applying the force? That curve that I was just showing you, we want to apply it downward on this piston pin, or this crankshaft pin here, to simulate kind of the force that's getting input from the combustion event. So the engine itself has obviously a piston that, I guess this animation might be better. the connecting rod is working on the crankshaft directly. So you can see here the connecting rod pushing on the crankshaft. This is not the same engine, but it's a similar configuration as it's a single cylinder. So you can kind of see that occurring here. So we are putting a downward force here because the force of combustion will push down on this. We're going to ignore all of the rotation of the crankshaft just for the time being. So we just want to apply this force as a function of time. So at 600 RPM, one complete revolution of the crankshaft would occur in 0.01 seconds. So that would be 10 times per second we would have a revolution happening. Let me check that, 10 or 100 times per second. We would have 100 times per second, apologies. So 100 hertz is what we would have for our input, basically. We're only going to simulate one cycle here, and what we do is we have the force versus time. So that's the force in the y direction here in global coordinates, and we're putting a negative because we want it to be compressing down. And you can see if we click off any point here, how it varies and reaches a peak around a time of 0.0527. Sorry, 0.00527. So about half, a little bit after half, which is what you'd expect based on internal combustion engine theory, but it's about halfway through the beginning and the end of the cycle. So all fairly complex background information, but we have some time varying load signal. This is the only thing that we want to simulate. So I've gone ahead and run this simulation, and you can see kind of what happens here. I will click play, and you can see how the deformation progresses. I will exaggerate here the deformation to kind of show you the crankshaft bending under the load. Maybe too much deformation scale. So this is the crankshaft bending under the load, and then the load getting released. So that is pretty predictable, as you might expect. What isn't predictable is what happens when you go at a higher engine speed. So what happens here is, because now this is a transient analysis, we did it at a very slow engine speed where we're only operating at 100 times per second. If we do 1,000 times per second, let's say 6,000 RPM, now our load signal will go between 0 and 0.1, where this one was 0 and 0.001. So 10 times difference. So 1 e to the negative 2 versus 0.1 as the load signal. Exactly same load signal, we've just exaggerated the time scale. So this is what it looks like here. We'll do directional deformation. This is what it looks like. I will exaggerate the deformation. This is what it looks like when we're just pushing down and releasing. Pushing down and releasing. And then when we do it at a higher rate, you're going to see some effects that are interesting. So you may have noticed that these crankshaft cheeks here are flapping around like crazy. So one thing that is interesting is the fact that because this is a transient analysis now, we do have the effects, the dynamic effects of the force coming into play. So what that means is there's an impulse as this force is getting ramped in. It's almost as if when we go faster, we're hitting the material at a higher rate, or we're basically applying this load at a faster rate. So that stress propagates through the actual component here differently, because now you can see the crankshaft cheeks here it's almost as if we're shocking it. This is what happens when we shock it. It's ringing because we're hitting it so hard. So this isn't a physical result. Obviously, this isn't what you'd expect to happen. This is just an artifact of the way that we're simulating it and the kind of the assumptions we're making to just do a simplistic simulation to get things started, where we're just pushing down here and we have some time varying load signal that we've gotten from kind of internal combustion engine theory, as we mentioned previously. So that's all fairly rudimentary, but now we need to apply this time varying load signal with some form of rotation here, so that obviously we're not pushing down when the crankshaft's at top dead center here. That's not correct in the strictest sense. So the animation that I started off with here is now that same time varying load signal. However, we have a rotational velocity imparted on a joint of the material or the component itself. So this rotational velocity is in radians per second here, and it corresponds to the rotational rate of this component. And what this does now is we're applying that same force, but we're going to be doing it in a way where the crankshaft is rotating. So you can see here the deformation now doesn't, the contour plot of the deformation doesn't really make a lot of intuitive sense because there's so much deformation here, or displacement. But what does make sense is the equivalent stress. So you can see now, once it loads, I'll be able to pan around. But you can see now how at bottom dead center of the crankshaft, that's where we see peak load. Apologies, I meant top dead center. This orientation is upside down, but you can see it here. Top dead center is when it's pointed down. I can flip it around to make it easier to view. Yes, so at top dead center would be like this. So you can see the crankshaft rotating now. Hopefully that's a little clearer. So there we go. Okay, so top dead center there, you can see how the crankshaft is rotating and the load is being applied because the most amount of compressive force is being generated as the crankshaft travels upwards and reaches top dead center. So now I've kind of explained to you the overview of how we've built upon applying a time varying compressive load, how we've added rotation into that, but I haven't shown you how to create this model. So we'll go ahead and do that, and we'll talk about each step individually. So we've booted up from our workbench the transient structural engine, and we will open that up and we'll import our crankshaft CAD. So we'll browse to that geometry file. Step works best here, step file format. So we'll open that up. And there's a few things that I'll do in real time, and there's obviously the solving process. The two more simplistic simulations without the rotation, they occurred maybe in 10 or 15 minutes of simulation time, and it almost took an hour on my local machine to solve the one with rotation. So that gives you an idea of kind of what the runtime would be for one of these types of simulations. So shortly here, the CAD geometry will import, and you can see we'll just play around here and look at it. So there's a few things that we need to do. We'll check the material similar to what we've done in the other videos. So just by clicking on the body here, and we've selected structural steel. just because this is a linear analysis where there's no elastoplastic effects. It's only elastic. It's transient, but it's linear material properties. So that's something that's important, and we're using structural steel here as the material properties for this, as that's probably fairly representative for a typical crankshaft. 4340 steel might be a higher strength version, and typical cast iron might be something you would use for a more or less expensive crankshaft. So that's what we've selected there. The next things that we need to do are we'll mesh the component. So we'll just right click on mesh here in the tree, the browser tree here on the left, and we'll click generate mesh. And I've used all the default settings for the mesh geometry, which by far is not ideal for the local stress concentrations in these fillet radii that are pretty critical for capturing the fatigue stresses in the material for these types of load cases. However, for the demonstration purposes of this tutorial video, I'm just using the default mesh settings. The simulation will run fine with these settings and converge. But obviously it's not going to give you the most ideal stress distribution in those high gradient, stress gradient regions. So we're just going to let this mesh here for a little bit, and now we have our meshed model, and you can see these are tetrahedral elements because it's a thick body. It makes the most amount of sense to do that with this body of a regular shape. If we had an axisymmetric type of component, we might use other types of elements, but or even a plate type component, we might use plate elements or shell elements. But that's what makes the most amount of sense for this kind of voluminous crankshaft here. The next thing that we want to do is go to our analysis here, and we want to add a transient structural. So we'll click on that, and that'll bring that up. And we want to add some connections as well, so we can insert, if we go to insert, we want to go to connections. So not joint load. You have to be on a specific coordinate systems. Here we go. So I guess we'll set up some of the analysis settings to begin with. So because it's a transient analysis, we need to define what's called a step time. And that step is the increment by which the analysis is now performing an iteration, the analysis engine. So instead of just giving you a final result for the deformed shape, it's calculating all these intermediate steps because our load signal is changing with time. So it makes sense that we have at least a load step or at least a iteration step for every time period that we're giving it. So the number of steps here is a little bit counterintuitive. This is the number of overall load steps that you want to do. So if you had some sequential operations, like say the crankshaft was going forward and then it was going in reverse, that's where you'd have multiple load steps. But we just have one load step, and we are going to have an ending time here that corresponds to the end time to complete one revolution. So at 600 RPM, that's 0.01, and we can get to that by just looking at 10 revolutions per second. Apologies, so that would be 0.1 for 600 RPM. And we want to have a time step setting here that's at least 10 times more fine than what our end time or what our initial step size is. So we'll say 0.001, 0.001, and 0.001. So that would mean that whatever this increment is here, so the increment between these time periods, so 5 degrees, that's what you'd want these numbers to be. So the initial could be 0.001. Your minimum could be a lot lower and your maximum could be this, but we're just forcing it to be that. And we can scroll through the rest of the settings. That's really all you have to adjust on the analysis settings. Our initial conditions, we want to make sure that the crankshaft is either stationary at the beginning of the analysis, or we can perform some calculations to see what the initial condition is. What we really want to do is just extract one cycle and simulate one cycle from a rotating engine that has the combustion events occurring. So the initial conditions, we'll talk about that in a little bit, but what we want to do now is apply some joints and connections. So we can say insert connections, and we are going to add a joint, and this is what's going to allow us to define effectively a cylindrical constraint. However, the joint is going to allow us to rotate the component and kind of apply some boundary conditions to that joint that forces some rotation. So we're supporting it on two main bearings, so these four surfaces. This isn't terribly important. This crankshaft, that's the way that it's supported. The flywheel mounts to this here, and some other part of the crank, maybe another bearing over here. But this is where the power is getting exiting the system from the crankshaft. So we need those surfaces there, and we are now, because we have a connector, we need to define a few things. The crankshaft is going to be the other side of this connector. Think of it kind of like a spring that you can define stiffness. So instead of between two bodies, we only have the crankshaft here. If we had the crankshaft and the connecting rod, we can say that this connector is between two bodies, but we're actually between body and ground, because we can assume that the engine block is just something that is, for the intents and purposes of this simulation, rigid. So it'll be ground, and we can say that our scope here is going to have those four surfaces, and the body it's going to automatically assign to be, because the ground obviously is this inertial reference frame, it now has recognized the body to be the only body in our model, which is the crankshaft. So this is important. There's other ways that you can accomplish this, but for a single component that's rotating, this makes the most amount of sense. We can also define a few things like changing the behavior from rigid to deformable, and that allows us to see deformation in the component, so we'll leave it like that. But the reason we've used this joint here, this connector, is so that we can apply a condition here in our transient analysis. So that is a joint load. Okay, and because we only have one joint, it's easy to select here. Once we open that up, actually, apologies, this should be a joint rotational velocity. I thought you can get to it from that. Insert, not a joint load. This is why. We forgot to tell it what kind of joint this is. So we've assigned surfaces here, and we need to say that it's a revolute joint. So by default, it will say fixed, and we want a revolute joint, meaning it's a cylindrical constraint. That's the only setting that I forgot to mention before we moved on from this menu. So we can say revolute cylindrical. The difference between these two is that one has an axial constraint and the other doesn't. But there's other versions of connector joints that we can select here. We'll use revolute. So now we can go back to our transient analysis and we can click insert and we can go joint load, and now it'll allow us to select the only joint that we have defined here. Obviously a rigid joint can have a joint load, so we're not going to actually apply a load here. We are going to apply a rotational velocity, and the rotational velocity that we want to apply coming from our calculation spreadsheet here is 62.83 radians per second. So we've just converted 600 RPM to radians per second. So 62.83. And now you can see how that has been applied to that joint. So we now have our joint set up, we have our rotation set up, we just need our force to be input here as an input to our simulation. So the way that we can do that is if we go to our transient analysis and we click environment up here, that'll bring all of our different types of boundary conditions, and we want a load in the form of a force, and we want to apply it on the bearing surfaces of the connecting rod. So we'll click apply. That's all fairly simplistic. However, the important thing here is that we want to define it by the components so that we can do X, Y, and Z individually. So if we're only going to assume that the force is totally vertical, we're going to ignore any connecting rod angle in this analysis, but we could easily add the X components of that as well. So I've converted, we don't have any information on the connecting rod length. So in order to find the X and Y components of this force, we'd have to know the connecting rod length to get a free body diagram and find the X component. We're just assuming it's all going to be in the Y direction because the connecting rod angle, we're making that small angle assumption. So if the connecting rod is very long, would be a good assumption, but I encourage you to do X and Y components, or in this sign convention here, yes, X and Y, it would still be X and Y. So now what we want to do is, you can see on the right, because it's a transient analysis, we can input tabular data here. So it auto-populates 0 for everything for the very first part of the analysis and the ending of the analysis, which is 0.1 seconds. So taking the data from this curve, I have some cells here that I'm just going to copy in. So, but this is the time varying between 0 and 0.01. So this is for 600 RPM. So we will do that. I'll convert it here for 600 RPM. So you can see that's between, not divided by 10, multiplied by 10. So you'll be able to see that here. I'll just paste the values somewhere intermediate. And I will copy that. And this is, process flow is a little bit tricky. I'll go back here to our model, and we'll right click on the time here at the ending, and we'll click paste cell. And that's going to populate everything here. You could have manually typed that in if it was a few, but this will save lots of time if you have many lines of force data. Similarly, I have the forces here. I know the sign convention showing it as positive in this graph, but we've negated it just to get the vector in the right direction, because up is positive. So we'll click paste here, and now you can see our force versus time populate, and you can see the vector that's being shown here graphically is downward, which is what we'd expect. We're looking at the engine kind of upside down right now. It actually should be like this, but for most people it's just easier to see the other way around. So we're actually pushing at peak force here, we're pushing up, or the crankshaft is reacting up effectively. So hopefully that makes some sense. So the next thing that we can do is run the simulation. For our analysis settings, we're missing a few things here. It's wanting our large deflection is on, and we can now just review everything before we click simulate. One thing that I will mention is the fact that when we go here, our temptation is to not use a joint and a connector. Some of you that are, let's say, experienced with the static structural analysis, you might have been tempted to come here and say, I want to, instead of using a joint and a connector, I want to impose a cylindrical support here and here. We can do that for the analysis where it isn't spinning. However, the cylindrical support, the sign convention is as follows. Y is the tangential direction, so that's around the circumference. X is the radial direction, and Z is the axial direction. So you want to make sure that you have the right constraints for that. But applying the rotation, people might be tempted to use a cylindrical support and then apply a rotational velocity. However, this joint connection method works much more nicely for getting the result that you want from this simulation. As the crankshaft rotates, you get peak stresses occurring halfway through the full cycle, fairly close to top dead center, which corresponds well with this pressure volume diagram, or apologies, pressure versus time diagram. Oops. So we'll go back to the simulation now that you've seen how to set it up. As I said, I won't actually run this, but to run, you'd right click and click solve. It may complain or give you an error message about large deformations, and that's why we've selected them in the analysis settings. So that's okay. But we have, just to reiterate, we've selected a CAD file, we've imported it, we've ensured the material properties are defined, we've added a connection between the crankshaft and ground, which is effectively the engine block that's not shown here. This connection is of revolute type, and this type of joint connector allows us to apply a rotational velocity to this joint. This in and of itself will generate centrifugal type stresses within the crankshaft. However, at the imposed rotational velocity of 600 RPM or 6.2 or 62.83 radians per second, they're not really substantial. What is substantial is the forces that we're applying in the downward direction. And if we wanted to invert that, we could, to simulate, I don't know, the tensile forces on the connecting rod. We're simulating the compressive forces on the connecting rod, but that's neither here nor there. So we have a time varying load signal. The data here just corresponds to every 5 degrees of crankshaft rotation, and there's 360 in total. So we have 72 data points ending at 0.1 seconds, which is 10 hertz, or effectively one cycle every 1/10 of a second. And then in our analysis settings, we have set our step end time to be that value there, what it takes to do one cycle, and our initial step time is a value that's less than that. It must be less in general. An order of magnitude would be a good idea to start with. But these are all things that are more advanced topics for convergence criteria in a explicit dynamic simulation such as this. So I just stay tuned for another more advanced video if you'd like to hear more about those topics. So that kind of overviews the setup of this transient structural simulation. We'll go back to the results for that particular setup, and we have the following, where we'll click play, the crankshaft is rotating, kind of animates slowly for the first revolution until it generates all those steps, or the animations for all those steps in your current view angle, and then it'll go a little bit faster. So we can see here at top dead center the bending is maximum. One thing that is interesting to note, the beginning you might see some flashing of some high stresses in the beginning. Those we can somewhat ignore. The reasoning why those are occurring is quite complex, but we haven't added any dampening or rotational stiffness into the system. So right now we're imposing that rotational velocity. However, it's going from a resting state to that rotational velocity in one instantaneous step. So that's why you see this big jump in stresses initially, is because there's an impulse of velocity that the component is seeing. The way that we can enhance this model to eliminate that is as follows. We could add a initial condition here that is an angular velocity. So instead of the component starting at rest and then accelerating to 600 RPM in one step, we can add an angular velocity here where it was always at 600 RPM as an initial condition. So I'll leave that for you to try on your own, but that's part of the reason there. You can see, if we go to another analysis model, you can see how the peak for the bending only model, where we're not including the rotation, the peak stresses that are occurring here of approximately, we'll probe here, about 0.2 MPa, so not a huge amount for steel for this load level, but these are the stresses that we're seeing. It corresponds to the load step that has the peak load, which is what you'd expect. Sorry, not the load step, the point in time of the simulation. So the peak load here is occurring at 5.277, and we have our peak stress approximately 5.3. So those values don't directly correspond to one another because we use the increment that was in the nearest 0.01, or rounded to the nearest significant digit. So you get the idea on that. So now, to kind of summarize, the most important thing that I would say is ensure that you have good input data, and if you're going to attempt to run a simulation this complex, you have good data for the load case, because often dynamic time varying transient load cases, it's hard to get good data for. The next thing is build up the complexity. You can see how we did the crankshaft bending simulation on its own, and then we added the rotation afterwards, and then we increased the rotational rate as well. So try and do it slowly first. I know it doesn't correspond directly to the load case because the load case will be probably tied to a specific engine revolution rate or a specific throttle amount or torque value, but as a kind of first guesstimate or first setup simulation, it makes sense to build the complexity up so that you understand where each setting plays a role, and what, when something isn't working or it isn't converging, you know that there was a known quantity that worked. The force application worked. Then you added the rotation and the model didn't converge. So it's easier to troubleshoot when you apply that type of process flow mentality to your simulation building or your model building. So I encourage you, if you're interested in these types of simulations, this is one of the more complex ones that we'll touch on, and it kind of combines a lot of the knowledge in the internal combustion engine itself, which I wasn't really diving into detail here in this particular tutorial video, but from the transient structural point of view, this is extremely powerful because we can look at a whole bunch of different parameters now and different stresses that are induced in a different way on the component, because we're not only just applying the load and seeing the maximum state. These things are time varying, and often finding at what angle of crankshaft rotation that maximum stress state is occurring is extremely important, because if the peak hotspot of stresses is in this location, we will obviously add some more material where we can to to address that stress issue. But you can see in the other scenario, where were we? In this one here. So we look at right here. So you can see now as it's rotating, we're going to have the peak stresses and the hot spots in different regions. So the bending's occurring on the crank pin there. So hopefully that kind of shine through here in the tutorial video. But yeah, it's an extremely eye-opening experience to do this type of simulation. I encourage you all to try it. If you have any questions, comments, feel free to reach out. The other videos are definitely going to help you. The other tutorial videos are definitely going to help you understand the more basic setup parameters, and this is more of an advanced topic. And please keep an eye out for future videos of more advanced topics of different realms of engineering and different analysis modes that you can access here in Ansys Mechanical. Thanks for now, and we'll talk soon.